So in the last video we built this we wrote this digits join function, right? So now we want to look at the reverse of this. So basically you should be able to turn 1 to 3 into 1 to 3. So, and to do that you can also use the same logic of powers, right? So if we have 420 and we divide it by 100, we should get we should get 4, right? So that's this, and when we say 420 mod 100, we should get the remainder, right? And the remainder is what we go with again, and we say 20 mod 10, we get 0, and if you say 20 divided by 10, we get 2. So we can split numbers. So to do that, let's start with a function called digits split. So now what this function is going to do, it's going to recurse. So but the signature is basically going to be take a number, an integer, and return a list of digits. So now just digit split number equals to split digit split prime, and pass our. So we'll define this in a where block. So what I mean by digit split prime, so takes an integer, which is the power, and the number you're trying to split, and the final amount. So you can also use a bit of composition here and remove this, right? So what would this function do, and what is this power argument? So this power argument is going to be our power, right? Now you start from 100 and you go all the way to 10 or 1, right? So that's basically what we want to do here. So if we say power, so now power and num. So I'm basically saying num divided by 10 raised to the power, right? And that should give us the digits we want, and we want to call this same function back on the remaining digits. So we would append to the list and say digit split. We'll reduce the power now, power minus 1. On the number mod 10 raised to power. So, and we need to have a base case, right? So the base case would be when power is 0. So the base case for when power is 0, we just return num, right? Because anything 10 raised to power 0 is 1, and num times 1 is 1. Cool. So now we just need to start this with a very high number. So for now, let's put it as 100 just to test the function. I said 100. So 10 raised to power 2 is 100. Yeah, so let's use the power as 2. So if we test this, when you say digits split for 20, it works, right? But if we try to do it for a bigger number like 8,420, we get this. So the tip is to start with a very high number. Let's say we want to have a magnitude of billions or trillions. So we need to start with something like 12, which is trillions. So 10 raised to power 12 is going to give you like, yeah. So, but to be on the safe side, let's go more than that. So we can do 12 times 12. Yeah, we can do for 144, but it's rare you get a big number. So when we do this, we are going to stumble in a new problem. Alright. And it is yeah. I get a new error trying to divide by 0, which is weird. Let's change it to a smaller number and try to debug this. Yeah, so this is what I was saying. So for some reasons, if I put a very large number, it just goes wild. So if I put 20, does it break on 20? No, it doesn't break. Aha, so that's where the problem is, isn't it? And now it just goes wild. It's weird how we're getting the very, very, very weird values, right? Yeah, it's probably because of this bracket. So then at what point does it break then? Let's try 12. It doesn't break at 12. Or if we go to 16 then. Yeah, it doesn't break at 16 either. So I think it has something to do with large numbers. Integer. I wonder how many bytes Haskell uses for numbers. So, but if we go by 17, still doesn't break. What if we go by 19? Yeah, so it breaks around 19. Yeah, it breaks at 19. So I guess integers in Haskell are around like have a maximum value, and the numbers are overflowing, right? So yeah, so for this I'm just going to keep it at the magnitude of 12. We should be fine enough for now for integers. So now we have a new problem, right? We have all these extra zeros that we don't want. What do we do with them? So we need to like perform some sort of filter on our list that is going to ignore any zeros. So we can, there is a function in Haskell called drop. So we can take drop, right, and say drop 2, for example, and 2 is gone. So let's say we drop 7. So you see where I'm going. We can keep dropping till we hit a non-zero value, right? So to do that, we need to create another function in this scope called drop leading zeros, right? So let's define that. Drop leading zeros. So it takes a list of integers and it returns a list of integers. So instead of even using the drop function, we can use like pattern matching over here. So we can say drop leading zeros if we encounter a zero, then return drop leading zeros on the rest. But if we don't, encounter a zero, just return the list. So this might work for us. Yeah, that's to be a function position, right? So now if we try this, yeah, so we get what we want. So we can say 2009 86. Yeah, it works exactly how we want, and we can say a very long number, and it works how we want.